My name is Fabrizio Pacini. I'm an account manager at Terra2 and currently I'm the project manager of the GeoAdapt. My company is called Terra2, was founded in 2006 with the support of the ISA Business Incubation Center, and our headquarters are in Rome. And our mission from the beginning is to provide support to researchers in science to use satellite data as information source in collaborative workplaces. And for this, we provide the cloud platform to support our users to transfer in production scalable software applications. So with our platform, we have supported the European Space Agency to develop the thematic exploration platform, that is a set of R&D activities started in 2016 to demonstrate the benefit of new techniques for large-scale on-demand processing of data. And in that context, we have developed the GeoAdapt exploration platform. That is a platform based on virtualization and federation of data. Indeed, the platform provides seamless access to cloud resources from private and public clouds, and also provide access to a huge amount of satellite data. So starting from the legacy missions such as CRS and ENVISAT, but also to the Copernicus Sentinels 1, 2, and 3. And the offer in terms of data is complemented by other missions like Cosmos Chimera, Spot, Landslides 8, and 9. And since 2018, we operate the GEP platform supported by our service providers that are all recognized experts from the European Earth observation sector, and they expose their services on the platform. So the primary focus of the GEP is on mapping hazard-prone land surfaces and monitoring terrain deformation. And the GEP supports the community with both on-demand processing for specific user needs, but also with systematic processing to address specific wide area interest analysis. In the slide that I'm showing you, see some, let's say, statistics, recent statistics on the GEP. We have a consolidated user community with about 3,000 registered users from 134 countries, and more than 350 users already carried out and are carrying out still projects on the platform by using the advanced services on it. The GEP provides data processing services and also allows to integrate users to integrate their own algorithm on the platform. The GEP processing services include basic services providing full resolution imagery and change detection products for rapid online visualization, as well as advanced services for both optical and SAR data processing. And the advanced services include classic INSAR diachronic analysis, advanced INSAR for persistent scatters and small baseline time series, and also digital surface model generation from satellite optical stereo images. And these advanced services will be the topic of the next of this webinar. So that we will see we'll have some specific talk later. The GEP as a service portfolio that has a public offering, so that you can find directly on the GeoAdapt website. And so this is how the GEP offer is organized in different packs according to the, let's say, complexity of the services that are required by the user. But also the offering of the GEP is available in the ESA Network of Resources portal. And this is an important instrument because it provides a privileged channel for science support, because it allows user to request sponsorship to the European Space Agency for starting their, let's say, work on the GEP services and understand if they are suitable for, let's say, the user needs. So if you are interested also in this channel, you can go directly to the page linked at the end of the slide that we will provide after the webinar, and there you will find all the information about the process for requesting GEP NOR sponsorship, but also for accessing the services directly via direct procurement with TerraDue. Now, so let's say the topic of today of this webinar is monitoring landslides with advanced INSAR and optical satellite techniques. We will have an initial lecture by Florent Provost from CNRS EOST, that is part of the scientific animation team of the JET, that will provide an overview of the INSAR and optical services for landslides that are provided on the JET and available on the JET. And then we have two guest lecture of practical cases. So the first one is from Dr. Thierry Opticofer of Terranum, that is one of the JET service providers, that is about detection and analysis of slope instabilities with advanced Earth observation services. And then we will have Dr. Deodato Tapete and Dr. Francesca Cigna from the Italian Space Agency and the National Research Council of Italy, that will present their work about Sentinel-1 INSAR for assessment of coastal landslides and ground instability in southern Italy. Now I will hand over to the presenters. Please, if you have any questions, please write them in the chat, because we will try to answer directly online during the talk, and then we will, after each talk, we will take some additional time for, let's say, answering to more complex question or to get additional question from your side. Okay, for me that's it. I hand over to Florian for the first lecture of the webinar.
For that, hi everyone. So I'm going to present a short introduction about ground motion services that are available on the JEP for landslide monitoring. So first of all, why being interested in monitoring the displacement of landslides? It's quite important to understand actually where and when landslides occurred, and displacement can be a good proxy to understand and to monitor where they occur and when they occur. So it can be also challenging because when it comes to where it occurs, it can be like very isolated slopes that are becoming unstable through times, or very like a large amount of slopes suddenly failing at the same time, which is quite difficult to monitor all together at the same times. And on the temporal evolution, it's quite critical to understand the cycle of landslides evolution, because it can transit from very dormant inactive motion to seasonal deformation, evolving to pre-failure and failure acceleration. And all of that, monitoring the displacement in time and space, can be used in to better understand mechanism and also the influence of different forcings on the slopes, and to develop mechanical models as well as early learning systems. So how to quantify the deformation of landslides? There are several techniques that are available. Some of them are ground-based, like GNSS, that have to be installed on the slope, which the disadvantage that it might be damaged or lost in the evolution of the landslide. There are some ground-based remote techniques, such as LiDAR or tachyometer, that can be installed in vicinity of the slope and take measurement of the whole landslide body. But same here, it has to be maintained, and can be quite tricky in some environment to access the sites and also maintain an instrumentation. And then there are several airborne and also spaceborne systems, such as radar satellites or optical satellites, that have the advantages that they will provide regular acquisition with a global coverage nowadays, and with a variety of sensor and techniques that can allow to monitor the ground deformation. So nowadays we have a huge variety of satellite constellations that provide different spatial resolution with different temporal frequency, leading to, for example, for Sentinel, to very large archive of several petabytes per year, with an open policy, which pose new challenges in terms of how to process all this data, how to access the data, and how to exploit the data automatically. So there are two main, as I was mentioning in the previous slide, there are two main techniques, which is the radar interferometry and the image correlation. So to be very short on that, and because there was previous webinar on SAR interferometry, and if you want to have more details information on the principle, you can look at them. But basically, SAR interferometry will consist in sending and transmitting a radar signal to the ground from the satellite, and then the satellite will record an amplitude and a phase. And as you repeat this thing several times at different time, you will have information on the amplitude and on the phase at different time, and the phase is proportional to the distance between the satellite and the ground. So if the ground is moving, basically, if you do the difference between the two acquisition, you will have the difference of phase being proportional to the difference of the ground motion. And basically, when you look at a phase at a single phase acquisition, you cannot see much information. But if you do the difference, you will get those kind of things that are interferograms, and each cycle of color corresponds to a magnitude of deformation, basically. So that's how it works, and it's quite precise and can record millimetric to centimetric measurement from satellites. The second technique is called image correlation. It can be used in different images, radar or optical, and the principle is quite simple. So basically, like here on the earthquake of Pelu, you can see that the right side of the image is moving upward. So you visually can see that, and basically image correlation will measure this shift between the two images, and then you will obtain the deformation between those two images. If you repeat that on many images, you will have the time series of the displacement. A bit of comparison between the two techniques. So they don't measure exactly the same thing. Radar interferometry will be sensitive to the deformation in the direction of the line of sight of the satellite, which means that it will be sensitive to east-west and vertical motion. It's very sensitive to north-south motion. It has a millimetric accuracy, and it can monitor small motion of millimeter to centimeter. It's not sensitive to cloud cover, so it's a quite interesting technique for that. And this technique of interferometry can only be used with radar acquisition. On the other end, image correlation can be used with radar and optical acquisition. It's sensitive to horizontal and vertical movement, depending if you used optical or radar images. But basically, it's sensitive to the deformation perpendicular to the line of sight of the satellite. It can monitor larger movement, ranging from centimeter to metric displacement, depending on the pixel size of your image. And in the case of using optical imagery, it will be sensitive to cloud cover. And here are some diagrams that explain you more or less when you can use INSAR and when you can use image correlation. And you can see that depending on the velocity of your landslide, you will be able to exploit radar interferometry or image correlation. And basically for any slow motion, you will use INSAR techniques, but when slopes are accelerating, basically you will need to like INSAR will not work so well anymore because you will lose coherence, and it might be interesting to use image correlation at that time. So they are quite complementary techniques. And coming to GEP, both techniques are available. So here you see the service packs that Fabrizio already presented. And in the advanced pack, you can see that there are several services that are INSAR services and as well optical imagery services that will provide time series of the displacement of your object. So some quick example of the outputs of the different services. Here it's a PSBAS service, which is a space interferometry service developed by Cenaria in Italy. And you can obtain this kind of results that are very like wide area results here in an area that crosses the French Alps and the northern part of Italy. And if you zoom inside these products, you will detect some slopes that are unstable, like here in Decazes in France, that are very slow-moving landslide, and you can have a clear signal and the time series using the PSBAS service. A different kind of radar interferometry service is snapping. It uses a slightly different technique, which is called PSI for permanent scatter interferometry. And this time the result will be only in some points that are very stable in amplitude through times that are called permanent scat, and it very well example in urban area. And here it's an example on the recent acceleration of Joshimat in India. So it's a landslide that created large cracks in the city, and some buildings were almost destroyed. Some people were moved, and so we monitored the formation of this area using this technique snapping on GEP. And you can see here that you clearly see the landslide in the ascending track. And here it's a view from the other side of the slope, and you can see that the toe of the landslide is clearly moving fast. And you can see also in the time series that some points are changing or accelerating in the recent years. Another example is here on the Embrun landslide in France, and you can see the difference between medium resolution snapping and full resolution snapping. So you have the both services, and you increase the number of PS when you use full resolution snapping. And here we use a service, and we compared it to one GNSS station, and you can see that the outcome of snapping is quite accurate in comparison with in situ measurement. Finally, and to be a bit brief on the image correlation, there is one service that is called JDM OPT slide, and it only uses optical imagery as input, but here it's a nice results that you can obtain, for example, in Peru. So it's a valley that is here. You can see that there are like some hills that are very steep, and some landslide developing on those hills. And if you run the service with the archive of Sentinel-2 images, you can clearly see the unstable slopes that are active at the moment, and you can see the direction of the movement in the horizontal plane, as well as the magnitude, which is about 100 meters from 2021 to 2023. And you also obtain the time series, so you can see that there are some acceleration for this slope in autumn 2022, and some continuous deformation for this one. So that's basically all the services that are available for landslide monitoring on GEP. And there is also a specific community thematic app called EO4Alps Landslides. And it's an app that is dedicated to monitoring landslides in the European Alps. And you have many different services that are available on these apps and that were developed specifically for monitoring landslide. And you also have products that were produced during this project and that are available for the member of the application. There was also some training materials that will be released soon on the JEP to understand what technique to use for which landslide, and to understand a bit better what are the advantages and disadvantages, or applicability and non-applicability of the different techniques. We try to make that quite easy to understand for one. And finally, there is also many new services that will be released soon to exploit the time series of those kind of services that I presented before. And one of them is called TimeSat, and it's basically classifying the different ground motion time series. So there are three classes, which are linear, quadratic, or bilinear with break trend. And from the output of GDM-OPT or snapping or PSBAS, you will be able to run TimeSat, and then it will provide a special categorization of the type behavior the point is undergoing. So that's quite interesting for further interpretation. So yeah, basically for more information on this app, you can go on this website, and there are also many information available on the GEP website. So that's it for me. Thank you very much.
Okay. Thanks a lot, Florian, for your talk. I leave the floor to Thierry Oppihofer for his talk about detection and analysis of slope instabilities with advanced depth observation strategies. Thierry?
Yes, good afternoon, everybody. Do you hear me? I hope so.
Yes.
So my name is Thierry Oppihofer from the consultant company Terranum, which in Switzerland, which is specialized in landslides and other natural hazards, and dealing since several years now more and more with Earth observation data, INSAR, the optical techniques that Florian just presented, but also some more landslide modeling oriented services, which we developed. Today, I have the pleasure to present you several case studies on landslides, which we realized using the different online services on GEP that Florian presented just before. And these services and examples were realized within the framework of the Year for Alps Landslides initiative funded by ESA, which Florian also presented just before. So I will be able to more or less skip my next slide. One thing that maybe is important is that the aim of this initiative was to foster the use of Earth observation data for different stakeholders dealing with landslide risks in the Alps. And to do so, we involved, within this project, we involved more than 70 authorities and stakeholders in the development and testing of the services. The services and products that are available on the platform, on the application on GEP, they can be divided into 4 different main categories. We have the ground motion services, which Florian presented just before, and which I will also focus today's example on. But we also have the other services related more to the automatic change detection of landslides that occurred after earthquakes or heavy thunderstorms. And we have also implemented in the framework of this project some services more related to the generation of the landslide inventories. This is this TimeSat service that Florian also presented. And we at Terranum, we were more involved with services related to landslide modeling with some volume assessment tools and some runout assessment tools. But as said, today I will focus on the ground motion services with my first example using the snapping service here in the medium resolution version. And our study area for that application is the Alpine resort of Anzère, near Sion in southwestern Switzerland. The town of Anzère, it's with the different chalets, it's constructed on a nice, very nicely exposed south to southeast facing slope. More or less on the valley sides, but unfortunately the entire town is affected by deep-seated landslides. Therefore, we used the snapping processing chain in the EU4Alps landslides on GEP to create ground motion maps. And for that, we processed the Sentinel-1 scenes that were acquired between 2015 and 2020 during the snow-free seasons for both the ascending and descending orbits. The snapping PSI service provides not only the average displacement rates, but also displacement time series for all measurement points. These INTs are ground motion maps that you see here. In the upper part, it's for the ascending geometry. In the lower part, it's for the descending geometry. Both show about 2 to 5 millimeters of movement per year. In the ascending data, where the satellite looks towards the east, we see an average movement of 3.3 millimeters per year away from the satellite. So meaning more direction to the east. On the descending data, however, we see an average movement of 2.8 millimeters per year towards the satellite. So again, more indicating a direction of movement towards the east. Combining these two data sets together leads us to a displacement rates of about 3-4 millimeters per year for the town of Anzère in the expected movement direction, which is controlled by the local slope morphology, so meaning towards the east or east-southeast. So here, the INSAR technique provides a very consistent data set that can be easily related with the local slope morphology and the expected mechanism of this landslide. My second example uses this image correlation and offset tracking technique that Florian also presented before, this GDM opt slide. And for that case study, we applied this technique on the Barmas rock and debris slide in the Val de Bagne, again in southwestern Switzerland. It's the same area as before. You see here on this picture, it's a very active site where the rock mass is strongly disintegrated and a lot of rockfall occur and debris accumulates, leading to a debris slide that threatens the communication lines, the roads, power lines in the narrow Alpine Valley. The ground motion map generated with GDM opt slide using Sentinel-2 imagery from 2017 to 2021 shows about 2 to 5 millimeter per day in the debris accumulation zone at the foot of the debris slide and up to 8-9 millimeters in the upper part of the landslide. On this side, we also have some ground measurements, and here we have periodic GNSS measurements, or GPS measurements, and we see very similar movement trends in comparing with the MPIC GDM OptSlide dataset. What is important here is to mention or to note is the difference in scale of the units that we use. We have here millimeters per day of movement, whereas before, in my previous example, we had millimeters per year. The third example I'm going to focus on today is generated not with a service that is online on GEP, but using a data set that has been provided by Tre Altamira as a third-party service or product that will be available in the EO4Alps landslides app. We use that squeezer data set, so that's it's a similar approach to other insert techniques. But and we apply this data. We inspect this data set here for the Pointe des Savoirs deep-seated gravitational slope deformation, also again in southwestern Switzerland. The Pointe des Savoirs deep-seated gravitational slope deformation shows different compartments that are characterized by different displacement directions and velocities. Here in this frontal view, you see clear signs of deformation of the rock slope and signs of activity. In the ascending data set acquired by the produced by the squeezer algorithm, using again Sentinel-1 data, we see displacement that range from 2 millimeters to 10 millimeters for different regions of the unstable rock slope. In the descending orbit, where the satellite is more sensitive to westward movement, we are able to map displacement rates of 5 to 10 millimeters per year in a highly fractured, disintegrated zone on the northwestern flank on the Savoirs, which you see here in this photograph. What is interesting in that case, since we have this crest of that is affected by the landslide processes, we have on one hand, we see the movement here oriented towards the northwest, and in the previous data set in the ascending orbit, we saw the movements more to the southeast. Integrating these data sets with the morphology of the landslide, we are able to delimit the different compartments or areas that move with different directions and different velocities. For each of those compartments, we computed the average velocity from both the ascending and descending data sets and combined then those line of sight vectors with the average slope orientation to compute the likely 3D displacement vector for each compartment. This information we will further use to interpret the mechanism of this complex unstable rock slope. To sum up, today we presented several applications of services and products available in the EO4Alps Landslides app on GEP. Our current portfolio of services will soon be complemented by other services like the TimeSat service, and also by the value-added products created by the project partners, including the squeezer and snapping full-resolution datasets. The EO4Alps Landslides initiative and the development phase are now coming to an end, but we foresee that the application will be soon accessible for the entire landslide community. So please feel free to write us or visit our website, eo4alps/landslides.eu. Thank you for your attention.
Okay, thanks a lot, Thierry. Let's see. So I don't see question in the chat. Is there? We can take I think, 1 or 2 questions, if any. Is there any question from the audience about the the presentation of Thierry? Yeah.
Hello, it's Sigrid. Thank you very much for your very interesting talk. And I was wondering about 2 things, very impressive results. And if you think about monitoring larger areas, do you have any kind of algorithms where you can basically identify the suitable regions? You know, if landslide inventories or movement analysis is also a lot about completeness, you know, and in a wrecked terrain,
Yes.
so radar is a little bit in some areas not so easy to do. So I'm wondering, is that your goal or the goal of this project to have some kind of regular monitoring of larger areas, but also including information about where you at all can obtain results?
Yeah, that's a really good question, and yes, that's something logically you need to be aware of the limitations of INSAR techniques or the optical techniques. And this is typically something that we also provide within the training material that is already available on the GEP website. Regarding to a map where the monitoring or ground deformation measurements are feasible with one technique or the other, we don't provide such a map up to now. It's not planned to provide this within the framework of our project now, but I think it could be a really valuable addition for understanding why you have data here, why you don't have data here, and how trustworthy are these are the results that you obtain.
Thank you.
There were also 2 questions now in the chat.
Yeah.
Can I quickly answer them?
Yeah, go on, Thierry.
Yes. Okay. So there was a question about if we use only the free INSAR data. Yes, the products and results that we present today, they are based on Copernicus data on Sentinel-1 and Sentinel-2 data. So these are accessible. And then limitations regarding vegetation cover. That's obviously one of the major limitations of both the INSAR tech, especially for the INSAR techniques, but to a certain point also of the optical techniques, which is inherent to the methodology of INSAR. There are some further developments looking at other satellites or other radars, other types of radar satellites, more using L-band, so longer wavelengths, which can penetrate a little bit better through vegetation, provided it's not too dense. And this can increase the coverage on natural slopes, but also slightly vegetated areas.
Okay, so just let me add that currently we are, let's say, evolving our service to be able to also process L-band satellites. So this is in the plan of the GEP. So hopefully by the end of this year we should have already test results. I think this will give additional tools useful on the GEP. I think we can now, let's say, go to last presentation. So I refer to Deodato Tapete from the Italian Space Agency. We just talked about the Sentinel-1 INSAR for assessment of coastal landslides and ground instability in southern Italy. So it's up to you, Deodato.
Hi, good morning, everyone. I thank the European Space Agency, the GEP team, Terra 2, Jean-Philippe Mallet for the kind invitation to present this use case that I have developed with my colleague from the National Research Council of Italy, Francesca Cigna. I will present today also on her behalf. It's about, as per the title, on the use of Sentinel-1 INSA data derived from very big and very long time series to address a specific use case, which is quite common in the earth science domain. So geologists are quite used nowadays to exploit INSAR time series to update inventories of landslides that are slow moving. We know that INSAR is very helpful in this regard. So if we talk about slow moving landslides, INSAR data from interferometric techniques are very helpful. So the use of GEP in this context is with regard to the right end of this workflow. So gathering the persistent scatter interferometry data that are input data into this component of a very typical methodology, which is quite well established in landslide inventorying based on INSA data. So we use INSA time series to update the state of activity knowledge of slow-moving landslides and their intensity assessment in order to evaluate the hazard and potential risk if there are elements exposed at risk due to these landslides, in order to contribute with a more consolidated and spread activity, which is based on optical data and photo interpretation in the detection from a visual inspection of optical imagery of landslides that may affect the study area. So according to a methodology that was published in 2013 by my colleague Francesca Cigna in Landslides Journal, it's possible to use persistent scattering interferometry data to update both the state of activity and intensity assessment of slow-moving landslides. In this context, so you see this applied using Earth, NVSAT, and RadarSat data, but the concept is applicable to any data, so also to Sentinel-1 data that you can access through the GEP. So you need to have a pre-existing inventory showing the landslides that affect your area with an associated classification in terms of state of activity and intensity according to the World Landslide classification model that has been already quite well established.
Maybe Deodato, in fact, we still see your first slide. And,
okay, sorry for that. So you should be able to see now the slides. So I just go back one slide earlier if you haven't seen it before. So this is the workflow I was mentioning before. So the data are used to basically input into this right hand of the slide. So in the workflow of using INSAR data to assess the state of activity, the intensity. And according to this methodology that I was presenting, you can use INSAR data to update the state of activity and intensity according to the World Landslide Community Classification System and the Cruden and Barnes 1996 deformation velocity and intensity classification. So the concept is basically that you have an existing inventory telling you where you have landslide bodies and what's their state of activity and intensity. If you use INSAR data, for example, obtained from Sentinel-1, or in this case, in the published paper using RadarSat data, you can update the information accounting for the velocity value that you have through the INSAR data, telling you if the body of that particular landslide is active or still inactive, and if it's intense or less intense according to a classification accounting for very slow and extremely slow motions. Typically, when you apply this type of a methodology to update landslide inventory, you can come up with various types of situations. So in terms of landslide detection and mapping, you can basically just confirm the presence of your landslide bodies as per your pre-existing inventory, or the INSA data are able to provide you evidence that suggests that the boundary has to be changed because the landslide body now is larger or is different than previously mapped. You can have also situation where previously no landslide bodies were detected, and thanks to PSINSAR data, you are able to identify and detect new landslide bodies, or in some cases, you do not detect any additional bodies. In terms of activity and intensity assessment, using SAR data, you are able to confirm or change the state of activity. I will show you an example on that. In other cases, you can confirm the known activity. And of course, there could be situations that because you do not retrieve any INSAR data, you are not able to tell anything more about the known landslide bodies. So in our use case with GEP, that we access through the GEP Early Adopter Program as part of a contribution that the Italian Space Agency, together with the European Space Agency, provided to the CS Working Group on Disasters. We have exploited and tested the PSBus Sentinel-1 processing on demand service developed by CNR IRIA that you have heard at the very beginning of this morning in the first presentation. So I'm not entering into the detail of this service. I just thank the GEP team for providing access, and of course CNR IRIA for having developed and shared it through the GEP. So our study area is in Calabria region, the same region in southern Italy where the previous methodology of landslide updating that I showed you before was developed and tested originally more than 10 years ago. In particular, we concentrated on the eastern part of the region, where we have a mixture of various air surface processes. This is a coastal area affected by marine terraces, where we know there's a susceptibility to coastal erosion with rockfalls, but also larger subsidence processes, also triggered by groundwater pumping and hydrocarbon exploitation. So there's an intermingle between natural and human-induced activities. In terms of landslides, this area has a known inland susceptibility to calanchi forms, so a specific type of landforms and landslides that are basically quite common in this type of marly clay deposit dominant landscape. So high hazard, but fortunately very limited risk, because fortunately very few situations see the intermingle between these calanchi forms and the presence of urban settlement. So in terms of data, we use the Sentinel-1 data, and in particular Big SAR data. At that time, 296 Sentinel-1 data in ascending mode were processed using GEP, and 283 from the descending mode. And I can tell you at that time, they were the longest time series processed in GEP and also published in the scientific literature, demonstrating that GEP has the capability to process real big data. So we identified the three main hotspots of deformation. We concentrate now on the zone B, where we identify the calanchi forms that, according to the hydrogeological setting plan dating back to 2016, there were several landforms already active in the center, and the INSAR data obtained from GEP confirmed that this area is pretty active with motions up to -4 centimeter per year, so high hazard, but as I said before, fortunately very low risk, because this is an area basically rural and unpopulated. Differently, along the coast, we found a dormant a landslide, which according to the data was reclassified as active, and in this area we have urban settlements, commercial activities, new properties built. So in this case, the landslide inventory update tell us that there's a potential risk. Finally, more inland, another Kalanki form, which was dormant, and thanks to the INSAR data obtained through GEP, was classified as active. So you see a very simple example where GEP can help in this regard in updating the landslide inventory, accounting for a wide spectrum of situations. So landslides that were dormant before and were classified as active based on insert data, and other areas that were already active and they were confirmed with more intensity. Of course, because they are Kalanki, we are aware that this is sometimes related to a normal weathering processes. So sometimes these motions are in reality more superficial than deep-seated. The spot C is more towards the coast along the promontory of Capo Colonna. In this case, INSAR data obtained through GEP corroborated a longer study that we undertook in the past years, starting from ERS1 into up to Sentinel-1. So the Sentinel-1 data obtained through GEP confirmed the presence of a widespread subsidence process. But interestingly, and that's a key point that I want to raise during this presentation, this information gathered through GEP needs also to be contextualized, given that in this area, as we studied in previous years, there's not only the subsidence process affecting the marine terraces as an effect also of groundwater pumping and hydrocarbon exploitation by humans, but there's also coastal processes affecting the coastline and in particular causing rockfall and collapses. So the deformation that we gather from the Sentinel-1 PISBAS service in reality shows also what happens in the months earlier than the collapse occur. So that's another key advantage of processing big SAR data through GEP that are very frequent in time. We are able to capture early precursor motions along the coastline before rockfall collapses. So in conclusion, what our case study tells us in terms of GEP capability. The PISBAS Sentinel-1 processing on demand service by CNR area can provide the geologist the needed input data to address the typical use case of updating landslide inventories, in the case specifically of slow-moving landslides. These data that are outputs from GEP become input data that can be value added based on a geologist's expertise in terms of associating the observed motions to real landslides and geotechnical engineering concerns. In case of presence of pre-existing inventories, you can use a GEP to run iteratively in successive intervals these analyses, so you can envision to update your landslide inventories on a regular basis. But cautious you have to be when you interpret from a geological point of view the massive amount of data that you gather from this service, because you have to contextualize accounting for the ancillary data and the in situ information that you have. This is all explained in the papers that we have published in the Remote Sensing Journal, which is open access. You have also the possibility to browse the article that we have published in the GEP blog about this experience. And finally, I just point out that you can access this couple of papers outlining the full methodology that we have used and exploited outside the GEP using the GEP outputs as our input to updated landslide inventory. And with this, I thank you for your attention.
Thank you very much, Deodato. Any question maybe for the presenter? In the chat or maybe directly online, if you prefer. Well, I guess your presentation was really clear. So thanks for that. Perfect. So if we have no more question, I propose to end up this webinar, the GEP webinar on landslide monitoring. I think we are perfectly on time at 2 o'clock. The webinar has been recorded, and in 1 or 2 days, it will be available on the YouTube GEP account, and there will be some information, in fact, how to get access to it. So thanks a lot for attending, and maybe keep in touch in the future for future application. Have a nice day. Bye.